No doubt there'll be one or two turning up after. And just as I said that, someone appeared. Okay, so we're essentially finishing off some loose ends here. We're going to look at applications of Taylor series. And essentially, this is the information that we're going to be using. For a well-behaved function y equals f of x, center that x equals a. So we're going to do a Taylor series of a function round about x equals a. What we're not going to do, thank goodness, is create the entire infinite series. What we're going to do instead is we're going to create these guys, which are basically Taylor's polynomials. So this one, for instance, goes up to the second derivative, and it's called t2 of x. This one here goes up to the third derivative, t3 of x. Practically speaking, we wouldn't expect you to do more than, say, t4. If you could do t4, you can do t40. I mean, it just means you have to do 40 derivatives and plug in 40 numbers and get 40 answers. And, you know, apart from the fact that that would take you forever, I mean, in many, many situations, you don't need too many terms from a Taylor's to get a reasonably good approximation to the function, at least for values that are of x that are close to the center, x equals a. So there are basically two kinds of questions that you're going to get. The first kind of question is going to be questions 1, 2, and 3. What you're going to get here is you're going to be given a function, whatever that is, and you're being then asked to find either t2 of x, or maybe they'll ask you to find t3 of x. I don't think they ask for t4, but let me do a quick check in case they do. 2, it's a 3 they want, it's a 3. Okay, so you're going to be asked for a 2t, 2, 3, could be asked in a different world for t4. And you're going to get those guys. And then the second part is you're going to graph what the original function looks like and what, say, t3 of x looks like. Now, when you do these things, let's just do a general question without being too specific. Imagine you had a normal function y equals f of x. Now, when we say well-behaved, what we mean is that it's just a normal curve, right? No vertical asymptotes, no weird things going on, just a curve, right? A normal curve. And let's suppose that we centered it here. Let's suppose that was the A guy. If I did t3 of x, it might look something. I might get a green pen, that would be nice. Where's my green?
When you first initially said for a well-behaved function, I thought you were going to say for a well-behaved child.
Well, some of your functions could be thought as naughty children and don't behave, but a well-behaved function is quite nice. So if I did the t guy, it might look something like this. I can't find green, so I'll do this. So what you're looking at here is that, no, there's a funny kink here, but somewhere from about here to here, do you see that the function and the original curve are pretty much on top of each other? Right, that's a good fit. That would be what I would mean if I said it was a good approximation. And essentially what that says is that if I use this Taylor's polynomial T3 and I found its value, the answer would be darn close to the real function's value. And that's good, because what that means is that for practical purposes, you can use a very simple polynomial to represent a really complicated function and still be able to get values that are well within the tolerance that you would like. So how does that work in a homework question? Well, here's a version of question 1. Suppose we are going to do 4 inverse tan of x, and we're being told that we're going to center it at 1. And we're being asked to find t3 of x. Now, T3 of x uses values up to the third derivative at a. So I'm going to start with my original function. You're going to get a lot of practice at differentiation in these questions. Well, the value of the function at 1, so it's going to be essentially that guy, is 4 times the inverse tan of 1. The inverse tan of 1 is the angle whose tangent is 1, which is pi upon 4. And that guy gets you pi. So there's your first fella. And I'll put a little circle around him because I'll lose track of them all. There's the first one. Now, since I'm wanting T3 of x, the Taylor's polynomial T3 of x, I need to go as far as the third derivative. So here's the first derivative. If you differentiate an inverse tan, you get 4 over 1 plus x squared. If you find the value at 1, you're going to get 4 over 1 plus 1 squared, which is 4 over 2, is 2. So that guy is equal to 2. How are we doing so far? So for that function, you get the value of it at 1. You find its derivative, you get its value at 1. I'm going to find the second derivative, evaluate it at 1. And lastly, the third derivative and evaluate it at 1. And what that's going to give me is the numbers that go here, f of a, f dashed of a, second derivative of a, and third derivative of a. Now to get the second derivative, right, I've got 4 over 1 plus x squared, and I want to differentiate that fraction. This is open to anyone. What differential technique can you use to differentiate that guy? There are actually 2 ways to do it, but which one would you choose? Both work.
Bringing that on the top and do a chain rule.
Okay, so that's where we'll go then. Oh, the other way is the quotient rule, if you're interested. So multiply by the power, reduce the power by 1, and then finish with the derivative of the inside function, which is 2x. That becomes negative 8x all over 1 plus x squared squared. So there's our second derivative. What I'm going to do here, because a little separation might help, I'm going to find the value of the second derivative at 1. It's going to be negative 8 times 1, and on the bottom, 1 plus 1 squared, which is what? Negative 8 on the top, 2 squared, which is 4 on the bottom, and the answer is negative 2. So our second derivative at 1 is negative 2. So we've got the value of the function at 1, the first derivative at 1, and now the second derivative at 1. And we only need one more, which is the third derivative, and we'll be done. Now, for this last function, it's going to be the ugliest derivative of them all. And the reason for that is basically just look at it, right? It's not a clean function. You could approach this in a number of ways. One way to do it could be, I guess, to write it like that, right, and do some kind of product job. That would work. Another way of doing this question would be to do this instead. Let me scroll that through. Is actually to FOIL out 1 plus x squared squared. And that's what you get. Now, it's not very pretty, but at least I have a way to deal with it. And what I'm going to do is the quotient rule. Now, if I'd left it in this format, which I certainly could do, this would be a product rule. But the other problem is, wouldn't the second piece also be a chain rule? And when you try and put all of that together, can you trust me, it just gets kind of unmanageable, right? It's just horrible. This is a bit uglier looking, but it will come out a little bit cleaner as far as being able to get the value of the derivative. So here goes. The top guy is going to be called F. The bottom guy is going to be called G. If you differentiate the top guy, you get -8. Leave the G untouched. Take away, leave f of x, and you differentiate this guy, you get a 4x and 4x cubed. And the whole thing is over that guy squared. Now that's not anywhere near pretty, but actually that's all we need. I'm not interested in that looking pretty. I'm not interested in even style points. So I'm not even going to multiply that out, collect like terms, look for things that factor, which you would typically do. Because the only thing I'm interested in is what's the value of that third derivative when x is 1. So I can just plug in 1 in all these places and off we go. And I think I'm going to need every inch of room. So it's going to be -8 times 1 plus 2 lots of 1 squared plus 1 to the 4. Take away -8 times 1, 4 lots of 1 plus 4 lots of 1 cubed. So that's the top line. And on the bottom, I'm going to be 1, 2 lots of 1 squared, 1 to the 4, all squared. And that's 1, 2, 3, 4. So that's -32. That's 8. And 8 is 64. 2 negatives make a plus, so plus 64. And the whole thing is going to be over 2, 3, 4, 4 squared, which is 16. So I have 32 over 16, and I get the answer 2. And there we go. We have found all the pieces. The value of the function at 1, the derivative at 1, second and third derivative evaluated at 1. So if we take a little pause in that, essentially what you have to do is find lots of derivatives at 1. Now the question was, find T3 of x. So T3 of x is f of a plus the derivative of a, x minus a, over 1 factorial, the second derivative of a, x minus a squared, over 2 factorial, and lastly, that guy. Now that is the generic formula for every T3 of x in the universe. Our particular one uses 1. So we're going to be finding the value of the function at 1 plus the derivative at 1, x take away 1 over 1 factorial. The next term is the second derivative at 1, x minus 1 squared over 2 factorial. And this guy is the third derivative at 1, x minus 1 cubed all over 3 factorial. F of 1 is pi. That guy there is 2, so it's 2 lots of x minus 1 over 1 factorial, which is 1. The second derivative at 1 is -2, so it's -2 x minus 1 squared, 2 factorial is 2. That guy is 2, x minus 1 cubed, and 3 factorial is 6. And just a little tidying up, I get a pi, I get a 2 lots of x minus 1. That cancels with that, but the answer is negative, so it's minus x minus 1 squared. That gets me a third, so 1/3 of x minus 1 cubed. And we have finished half this question. This Taylor's polynomial, Taylor's T3, that guy is going to be a good fit to the original function, at least near to the center, right? So near to 1. Okay, any opinion, any comments on the process? Do you feel it's kind of just repeating yourself until you're finished, right? Find the first derivative, get the answer.
I have a
Find the
feeling.
second derivative. Yeah.
I have a feeling there's going to be like 15 of these on the final.
No, you're totally wrong. If you get one of these, there will be one of these in the final, just by the sheer amount of work. The second part of it is actually pretty straightforward. We are going to plug this guy into Desmos and graph it, and this guy into Desmos, and we're going to compare them. And in the homework, what they do is they give you like 4 pictures, and you pick the one that looks like it, right? So that's the easy part. So I'm going to nip over right now and set that up, and let's see what it looks like. Now, going to have a little bit of an issue here, I think, with the inverse tan, because I can't write -1 because it probably thinks I mean power. So I'm going to go for arctan. Why is it capitals? I told you I don't want capitals. Arctan. That looks like it'll take it. X. Okay, there is 4 times arctan of x, 4 inverse tan of x. That's good. And now I'm going to put in T3 of x, and it was equal to pi. And 2 lots of x minus 1. Do you notice that you don't FOIL everything out? You just leave it in this kind of half-done format. You know, various powers of x minus 1. There's the second guy. Well, actually, if you look at it right now, do you see it's a pretty good fit already? See the red guy? That's only T2 we're looking at here. So I'm going to add on 1/3 x minus 1 cubed. There. So adjust the window a little bit. There. Move the center over to 1, roughly about here, right? Would you agree that at least close to 1, aren't both the original function 4 inverse tan and our polynomial so close to each other that you can't even see the difference? Is that amazing that a tan function or an inverse tan function can be represented by a polynomial and represented really quite well? Any comments on that? Does that look interesting? Kind of cool. Right, now, a lot of work, but the net result is something quite good. Now, while I've got this guy in front of me, let me tell you some of the truisms. This one was centered at 1. At 1, it's perfect. At close to 1, it's really good. But as you use values of x, roughly around about 2, can you see it beginning to diverge a little bit? A little separation. By the time I get to 2.5, would you agree even an engineer would be a bit worried about the difference here, right? If I had that was a bolt and that was a hole, I don't think the bolt's going to fit in the hole anymore, right? You could probably get away with it down here, but you're not going to get away with it up here. And if you look at the other side, you see they're pretty good. We're 0.5 good. Round about here, can you see the drift? But if you look further, really a long way away from 1, right? Can you see over here? It's ridiculously long. So Taylor's polynomials are really good close to the center. This one was centered at 1. But as you drift away from 1, don't you get less and less accurate until you can actually see the separation, which is not good. Any questions before I show you another one? Are we good? Right. Let's try one more. Take me a few seconds to find where I am. Here we go. I tell you what, I'll pick my own, that way I'm not wasting your few opportunities to do it on your own. So I'm going to pick a pretty nice function. So I don't need to worry about differentiation. I'm going to pick sin x. I'm going to center it at 0. And I'm going to do a t4 of x. So f of x is sin x. And the value of the function at a, which is 0 in this case, is the sine of 0 is 0. The derivative is the cosine of x. F dashed of 0 is the cosine of 0, which is 1. The second derivative is differentiate that guy, and you get negative sine x. And the second derivative at 0 is 0 again. And then I'll do the third derivative, which is negative cosine x. And the third derivative ends up being negative 1. And okay, let's do it t5. So the fourth derivative of x is 2 negatives make a plus. Oh, you're back to sine x again. So the fourth derivative at 0 is 0, and one last one because I've changed it to t5. You get this guy, and you differentiate that guy, and you get cosine x. And that guy ends up being 1. So sine x up to the fifth derivative evaluated at 0 gives me all these values. Now, if you want to find t5 of x, in this case, it's going to be f of 0 plus the derivative at 0, x over 1 factorial. Technically, I should be saying x minus 0, but that's just x, so I'm not going to bother. I'm going to add the second derivative at 0, x squared over 2 factorial. Keep going. Third derivative at 0, x cubed over 3 factorial. Fourth derivative at 0, x to the 4 over 4 factorial. And finish on fifth derivative at 0, x to the 5 over 5. And this one is actually a Maclaurin series, but Maclaurin series are really just Taylor series centered at 0. So we still call this guy T5. Now, when you start putting in the numbers, something interesting happens. That guy is 0. This guy is 1, so it's 1 times x over 1 factorial. That guy is 0, so I don't care what the rest are. You're still going to get 0 when you're finished. That guy is negative 1 over 3 factorial. That guy is 0, so I don't care what the rest is. And that last one is 1, x to the 5 over 5 factorial. So 1 over 1 factorial just gets you x. Negative 1 over 3 factorial gets me 1/6. That gets me 0. And 5 factorial 620 is 120. Here is T5 of x. Maybe unlikely, but I'm going to tell you that that polynomial is going to look like sine x at least close to 0, right? So you can imagine starting at 0 and drifting either side. This polynomial is going to look like a sine function, and it should be a pretty decent sine function. We are going to find out how decent by letting Desmos draw it for us. So the original function is sine x. Let's do that. There, nice sine x. I'm going to do y equals, and I'll type in all the pieces. We have an x. We have subtract 1/6 of x cubed. And then we're going to add 1/120th x to the power of 5. And okay, it's not much good over here or over here, but let's restrict where we look. Okay. Would you agree that that's a pretty decent fit as long as you're using x's between what, -1.5 and +1.5? Would you agree it's a really good fit for that middle chunk? Pretty good. Now, does it drift? Yeah, all of them drift. And do you see it doesn't take long before the drift is really bad? So it's like I do really good and then I kind of fall apart. And then if you go the other side, almost like a symmetric thing, right? I do really good and then I fall apart. If I wanted to make this fit last longer, all I would do is maybe find t of 20. Imagine, I'm not doing it, right? Like imagine we did it, t of 20. That would be a great fit, maybe all the way out to +3 and -3. And if I wanted an even better fit, couldn't I do t a million? Well, I wouldn't, but wouldn't you get a computer to do it? You can
In that case,
base it.
could you, oh,
Say again?
in that case, could you move the center and then just get an idea of what it looks like at that point?
Yes, that's what you do. So if you know that you're not going to be working at 0, most of your calculations are going to be over at like 20 radian for whatever reason. Couldn't you just change the center to 20 and you get a great fit there? Yeah, that's what you do. Now, it's okay to say it's a good fit, but you really want a number on it, don't you? Like, how good a fit is it? So that's where I'm going next. We're going to try and figure a way of putting a number on how good a fit a function, a Taylor's function is. So take a new page. The function that we're going to look at right now is sine x, and we're going to find out how good that guy is. And we know it's centered at 0. So just graphically imagine 0. And I am going to try and find out how accurate it is if I only use values of x in the range, say 0.5 to -0.5. And we know that was a good fit. If you went back to me a picture, you would see both of them almost on top of each other. Now, it's not a perfect fit. It's not correct to 2 billion decimal places, right? There is some difference. It's just so small you can't see it. But we would like to know what that difference is, right? And there is a function that we use called the remainder function. And the remainder function is the difference between the real value at x and what the Taylor's guy says at x. And we stick absolute values around everybody just so that the answer is positive. And I would like to know what the error is, say, at 0.5. Well, the error when x is 0.5, the remainder function at 0.5, is the value of the function at 0.5, take away that guy at 0.5. And I'll do this over at the side. The value of the function at 0.5 is, the real value is that guy. And I'm going to set this guy up. And we'll do it on the calculator. Here we go. So although you won't see the white thing, you will get at least to see the calculator that I'm doing it on, right? So are you looking at the emulator? Is that what you're seeing? Can you see a TI-84 calculator? Right, that's what I'm getting at. Okay, so the sine is 0.5. Well, I guess I should make sure I'm in radians, which sounds silly until you find out you're not. Okay, and I am. So I should be able to do the sine of 0.5. And the answer is, well, has a lot of decimal places to it. So I wonder how many I need. I'll write down all of them. Kind of overkill. 479, 4255, finishing with 386. And I'm now going to find what T5 is, right? The Taylor series 5 at 0.5. And what that is, well, our function was, let's say, x, so that's 0.5. And then we take away 1/6. Oops, let me go back. It's just a good idea to put brackets around things because you're never quite sure order the calculation. So take away 1/6, 0.5 cubed. And then add 1/20th, 1/20th of 0.5 to the power of 5. Right, now I hit enter. That calculation is what the Taylor's 5 estimate is. What would you be impressed by? Good to 3? Would that be pretty impressive?
Yeah.
Any? Well, let's find out. Assuming I didn't hit anything wrong. 479, okay, 0.479, 427, 7. I won't write any more down. Right, let me return back. Whoops. Let me return back to our screen and show you how good that really is. Did you notice it's the 6th decimal place where things went astray? Here, it was 5, and we got 7. So it's really good to what 5 decimal places, and even on the 6th decimal place, it's not miles away. So if you want to find the sine of x, and the angle that you're using is somewhere between a half radian and plus or minus, if you could memorize this polynomial, couldn't you get the answer good to 5 decimal places? Just by using a cubic. That's pretty impressive. Which is why I think the TI-84 does exactly what that is. Can you imagine the TI-84 just has programmed in it, maybe T20 or whatever, for the sine function. So when you say sine is 0.5, it just goes there. It might do a shift to center, you know, if you say the sine of 42. But there's ways around that. Can't you just subtract 42 until it's within the range minus 2 pi to plus 2 pi and just do the same guy as you always would. So I think that's pretty impressive. Now, at this side here, the error, right? If you take one away from the other, the error between these two guys, and I'm going to just stop here, right, is 0.0000, well, if you round it off, it's 1. Oops. 0, 1. Now I'm going to do that fella. And that happens to be the sine of negative 0.5. And I don't need the calculator for that because I know what the answer is going to be. It's going to be negative 0.4794255386. And now I'm going to find T5 of negative 0.5. And we'll see what that is. I should be able to do it by going second entry and then just going to each of these numbers and changing them to negative 0.5s. And insert a negative. There we go. Insert. Did I hit insert? I don't know if I did that. Hit insert, a bracket, and a negative. And then go to the other side here. Yeah, it probably would have been quicker just typing it from scratch, but too late now. And this time, I screwed up. I just know I did the calculation wrong. All right. Okay. When in doubt, just do it the long way, less mistakes. Negative 0.5. Subtract 1/6 times negative 0.5 cubed. Add 1/20 times negative 0.5 to the power of 5. No? What did I do wrong? Let's check it. Looks good. Kind of screwed up that much. Let's check what I typed.
Well, it would be the absolute value of it, right?
Yeah, but that would only make the answer positive. It's the 0.479 that I'm unhappy with. And I think it might be that. Let me check it. No. Well, what am I worried about? It is the right answer. I'm looking for a small answer. That's not what I should be looking for. Shouldn't I be looking for an answer that's the same value as the sine of negative 0.5? And the answer we got was negative 0.479427, and I'll stop there. Actually, by symmetry, I could have guessed it. The error on this side is also 0.000001. Now, what I can also say then is that the original function and T5 are very, very close to each other. They're only like the 6 decimal place out, which is pretty good. The next thing I can tell you is this, that the maximum error that you can get by using T5 of X is 0.000001 for all values of X in this range. And the reason why I can say that is, weren't these the two extreme furthest away from zero you're going to get? And isn't the rule the further from zero, the less accurate? So if that's the less accurate you're going to be, that's the maximum error. So we now have a way to say, not only can you use that and get a good approximation to sin X, if you're only going to use values of X in the range 0.5 to negative 0.5, I can tell you that whatever number you use between here and here, your answer is at worst going to be that out. And if you picked a number closer, it would be even less error, right? That's the worst case scenario. So if I went and chose, I don't know, 0.07, I bet you the two answers would be almost indistinguishable, right? Like 20 decimal places. That's pretty impressive. Any questions? We good?
Just trying to keep my head above water.
Okay. Well, we basically covered all the kinds of questions that you're going to do. I'm just going to choose another one where we do that error band thing and show you what it looks like. So here's a function that we've got set up, and I'll show you the homework question and how it's set up, and then you can kind of work from there. It's going to be, I think, question 4. Yes, it is. So in question 4, you're given a function. I'm not sure what you're saying here, so let me make sure that I'm on the right thing. Right. In question 4, you're given a pretty mundane function, x to the negative 9, and you're being asked to only use values of x in the range 0.8 to 1.2, and you're being asked to find T2 of x. In part B, you're being asked to find the maximum value of the remainder. And the way they write it is like that, and you put the number in the box. So as long as x is in that range, if I use T2, what's the worst error? And then part C is they give you some graphs where you plot this function and you choose the one that looks like it. So let's start with, well, the fact that we're doing T2 is kind of nice. And I forgot to tell you where it was centered. It's centered at 1. So f of x is x to the negative 9, which is fine. But it's kind of easier for evaluation purposes to call it that. So the value of the function at 1 is 1 over 1 to 9 is 1. A little circle around it. However, if you want to differentiate a function, this is nicer. Multiply by the power, reduce the power by 1. And that can be then rewritten as that guy. And when you find the derivative at 1, you get negative 9 over 1, you get negative 9. That's the second guy. Last one. Power rule, multiply by the power, reduce the power by 1. Rewrite it in that format for calculation purposes. And the second derivative at 1 is 90 over 1 to the 11, which is 90. So the function that we're dealing with is that guy. And it's centered at 1. So to get t2 of x, it's the value of the function at 1 plus the derivative at 1, x minus 1 over 1 factorial, and the second derivative at 1, x minus 1 squared over 2 factorial. That's the Taylor's polynomial for t2. That guy is 1. This guy is negative 9. This guy is 90. 2 factorial is 2. So we have a 1 minus 9 lots of x minus 1 plus 45 x minus 1 squared. And that's t2 of x. Now, how do we get the maximum error? That's the second piece of the puzzle. That's question A finished. R2 of x is the value of the function. Take away the estimate, and you stick absolute values around everywhere. Now, to get the maximum error, what you do is you find what this is equal to at the 2 extreme points. And whichever one of these two gets you the biggest answer, that's your maximum error, right? That's the worst case scenario. So I'm going to have to do 2 different calculations. I'm going to have to find what that guy is equal to. So it's going to be the value of the function at 0.8, take away that guy. And then at the other extreme, I'm going to find the remainder value at x equals 1.2. Which is that guy. So on my calculator, I'm going to find out what this is. I'm going to put the answer there. Then I'm going to find out what this one is. I'm going to put the answer there. Whichever one of those is the biggest is the maximum error that you will get in that range. So we are now going to do our calculator thing. Hopefully, won't have a problem. So I need to find x to the negative 9 at 0.8. So in brackets, 0.8 to the power of negative 9. So that's the f of 0.8 bit. Then I'm going to do take away, and I'm just going to put brackets around it because that's the easiest way of doing this. And it's 1 minus 9 times x minus 1. So what's that? 0.8 take away 1. Finish off the bracket. Yep. And then add 45. 0.8 take away 1 again, but this time we're going to square it. And then finish our brackets. So that's the error at the x equals 0.8 side. Ooh, that's not good. That's good. Yeah, that's good. We try something. Wow. Okay. I'm not wrong. It was just a horrible answer. Would you agree 2.85 out is not a good answer? It's not very accurate, but I'll put it in. Now, if I go and I do the other one, which is at 1.2 side, I might be able to do it by simply doing that guy and then just changing all the 0.8s into 1.2s. And I get 6.45 and stuff. Now, they have an answer in 19.2, which I'm not too worried about, and I'll tell you in a moment why. First thing is, the maximum error, according to my calculation, is 6.45. So what's that telling me? It's telling me don't use a Taylor series to approximate this function, because you are not going to get a very good answer, right? Now, you might think, why is that not doing a good job? And then we'll talk about the error issue. If you sketch x to the -9, it looks like that. And we're centering it on 1. Okay. There is a vertical asymptote happening here. Vertical asymptotes are bad news for Taylor's approximations. Functions are not well behaved when they are near to vertical asymptotes, because don't functions zoom off to infinity? Bad news. So there are actually 3 things that you should avoid ever doing a Taylor's on. Do not do any function that's close to a vertical asymptote. Yeah, it's okay doing it way over here if it's miles away, but not close. The second situation is don't do it when you get a function that looks like that. You see these little these things here, they're called cusps. Don't do a Taylor's approximation anywhere near one of them. You'll get horrible answers. And the third one is, do you know that there's some sinusoidal curves that go like this? Do you know the ones that zigzag up and down really rapidly? Don't go anywhere near those guys. So when we talk about well-behaved, we're really saying don't be any of these guys. We're saying just be a boring curve. Boring curves are good. Don't be vertical asymptotes or near me. Don't be cusps or anywhere near me. And don't be a ziggy-zag that goes up and down infinitely often. Now, they had an answer, I think it was 16, no, it was 19. They had an answer of 19.2085 and some other stuff, right? So why is my answer like 3 times out? They do a different way to calculate this. There is more than one way. I'm doing it the pure numerical way, just evaluate at the endpoints. If you use, I think it's called Taylor's formula, you can use it to estimate this answer. In Taylor's formula, you use, in this case, the third derivative and some other calculations, and then you have to estimate what the biggest value for the derivative is in a certain range. And because of that, you introduce a lot of guesstimates. And so it's not uncommon for these two to differ by quite a lot. But I've fixed it so that WebAssign will take my version of the answers, so you won't have a problem. In a way, it doesn't matter. If I say, oh, you're going to be plus or minus 6.45 out, or if I say you're going to be plus or minus 19.2 out, would you agree you're not going to use it in either situation, so it doesn't really matter, right? Yeah, it's a warning sign not to use it. So I think we should finish with, well, too quick. Is there anything about what we did there, apart from the fact I get really worried about these until I check the answer? What's going on? Are we still hauling in there, Calvin?
Trying, definitely
Okay.
trying.
Right, for our last one for today, and then we can spend some time getting ready for this final. Let's pick one where the numbers come out relatively nice. So it's probably going to be the last question. And it is. A version of question 6. The function you're going to deal with is x sine x, which is not a bad curve. It's centered at 0, which I like. And we're only going to use values of x in, this is quite a large range, right? Negative 0.9 to plus 0.9. And we're being asked to find T4 of x. On this question, I'll show you the third piece of the puzzle, which is the graph choice. I haven't shown you that yet. So, this function is that, and the value of the function at 0 is 0.
I feel like I struggle most with the questions that aren't centered at 0.
I like the centered at 0. Is it something about the 0 that throws you?
No, it's when it is 0, I feel like I'm fine, but not 0, then it's kind of hard for me.
Oh, yeah, the non-zero ones, centered at 1 or pi or something.
Yeah,
I hear you.
fine.
Now, if you want to differentiate that, can you trust me that you're going to have to use a product rule? So I'll call this F and I'll call this G. So you have that combination. And this guy is 1 times sine x plus x times cosine x. And that's the first derivative. And the value of the first derivative at 0 is, well, still 0. That's kind of boring. Second derivative. Differentiate this guy, you get cosine x. And to differentiate this guy, you're going to do a product rule. So f dashed g plus f of g dashed. And so you're going to get a cosine plus a cosine, so that's 2 cosines minus an x sine x. And the value of that second derivative at 0 is 2 cosines, which gets you 2 minus and nothing. So 2. 2 more to go. The third derivative, that guy there is going to get a negative 2 sine x's. You differentiate this guy, it's a bit messy, but you're going to get negative sine x, negative x, cosine x. And so you're going to get negative 3 sine x's minus an x, cosine an x. And if you evaluate the third derivative at 0, you're going to get 3 lots of none, that's still nothing. Oh, you're going to get a whole load of nothings. And the last one then, you differentiate this guy, you get negative 3 cosines. If you differentiate this, you're going to have to do a product rule again. So minus 1 times the cosine of x minus x times 2 negatives make a plus, so you're going to get that. So you're going to get negative 4 cosine x's plus an x sine x. And that, evaluated at 0, gets me negative 4. So all the different derivatives have now been calculated. We've got this one, this one, this one, this one, and finally this one. So I'm now going to put them together to get T4 of x. It's going to be the value of the function at 0 plus the first derivative at 0x, second derivative at 0x squared, third derivative at 0 x cubed. And lastly, fourth derivative at 0 x to the 4. Now, that guy is 0. That guy is 0. That guy's 2, so it's 2x squared over 2 factorial, which is 2. That guy is 0, and that guy at the end is negative 4 x to the 4 over 4 factorial, which is 2 times 3 is 24. And we have t4 of x. Cancel that down, you get x squared. Put that together, you get 1/6 x to the 4. Done. I mean, it's a little bit time consuming, but at least it's a process, right? You differentiate, you plug in 0, and then you keep doing it until you get to the fourth derivative. And once you've got all the numbers associated with it, you plug it into the formula. Anything that's 0 gets killed off, anything that exists, you tidy it up. And that is going to be our approximation. Now, we are interested in now finding the maximum value, right, of the error, that guy. So we're going to find the value of the function, and we're going to take away t4 of x, and whatever the biggest answer we get for values of x in the range negative 0.9 to positive 0.9, whatever the biggest answer we get is the maximum error. So I'm going to evaluate it at 0.9. And then I'm going to evaluate it at positive 0.9. So that's going to be the value of the function at negative 0.9. Take away that guy at negative 0.9. And then this fella. And that involves me hitting buttons on a calculator and hopefully not making any mistakes. So I'm now going to return back. I should remind you by right outside that the function that we are approximating is that guy. So let's nip over and see what we have. Right, we have the value of the function. Let's do the 0.9 one first. So what's that going to get me? It's going to get me 0.9 times the sine is 0.9. So that's f of x bit. Take away, inside brackets, x squared. So that's nothing 0.9 squared. Subtract 1/6. And it's 0.9 to the power of 4. I should be able to do it like this. And I'm expecting a reasonably accurate answer. And that is pretty accurate. It's 0.00434. Now, I'm going to evaluate that same thing, but at negative 0.9. So, negative 0.9, the sine of negative 0.9. Subtract in brackets. I'll need another bracket for negative 0.9 squared because I'm a bit worried ordinary calculation might screw that up. Then it's going to subtract a 1/6 of negative 0.9, again in brackets, to the power of 4. And I get 00434. I know that every question we've done so far, it ends up that these two answers end up being the same value. I don't want you to get caught up on the idea that that should be the case. They just happen to be in the questions we've done. That this error and that error are exactly the same, right? One might be positive, one might be negative, but apart from that, it doesn't really matter. That's important to realize that if you change the boundaries, say if I made that -1 or I made that 0.5, these errors would then be different, right? So in this case, I don't really have a choice because both of them are the same. So the maximum error is 0.00434. And WebAssign says that the answer is 0.02, so they're about 5 times bigger, but that's fine. Actually, this way is a little bit more accurate. So far, so good. Find all the derivatives. Use the formula to get T4 of x. The remainder is the difference between the real value and T4. Evaluate it at -0.9 one extreme. Evaluate it at +0.9 the other extreme. The biggest answer is your maximum error. Now, the last piece of the puzzle is that they ask us to graph. That guy. Well, at least graph it in the range negative, where are we going here? -0.9 to 0.9. So we are going to graph our function in that range. And that's really just Desmos. So let's kill that because I don't need it anymore. There's Desmos. Are you looking at Desmos? Can you see Desmos? No. Okay, so I'll have to go back out and in again. You see Desmos now? Right. So absolute value is a bit of a pain. Oops, forgot some. Have to type in y equals. Now, absolute value, if you click on this guy, you'll find it there. And f of x was what? X sine x. Interesting function. Take away, put a bracket around it. X squared, this is me now doing T4 of x, minus 1/6 x to the 4. Finish my little bracket. That's a bad place to put my bracket. Finish my little bracket. Now, do you see this weird U-shaped function? What that is essentially telling us or showing us visually is what the error, right? The difference between the real answer, which is the first bit, and the polynomial T4, the other bit. And the reason it is really, really flat at the bottom is because anything near 0 isn't the error very small. So that's basically showing you what the errors look like. Do you know when you get to a value x equals 2.5, can you see the error is huge, right? Plus or minus 1.7. No, it's not very accurate. Now, if I change my scaling just a little bit, let's be silly about this. Can you see how accurate it is from roughly 0.5 and minus 0.5? Look at that vertical scale, tiny, right? The error is almost negligible, but it doesn't take too far, does it, to go whoom, shut up. And that's pretty much it. Oh, we've got something in chat. What should I do? And we've done this question already. Well, I guess I've finished it twice then. Unless that was a previous question. Any questions before we start looking a little bit, you know, talk about the final, getting ready for the final, so on? Well, you've survived. First thing I would probably say, which most people will agree, is that if you talk to anyone who's done Calc 3, most of them will say that this section, this chapter, is the worst of them all. And that's just a general truth. Not everyone, of course, there are always exceptions, but in general, that's what they would say. Now, that doesn't, I guess it's tough, but because it's the last thing you do, don't let it depress you from all the other stuff that you found relatively good. Because if you just focus on the negative, you're in the wrong frame of mind, right? So, you know, the test consists of lots of questions. And not like Calvin thinks 10 of these guys and nothing else. That's not a fair final, right? Just by the amount of work in these, you realize that you're only going to get one of any kind of question, including this one, right? You're not going to get 5 questions where you find arc length, right? You're not going to get 4 questions where all you do is partial derivatives or whatever it might be, right? Each major topic, if it gets touched at all, is typically not going to consist of more than one version of it. That way we can cover as many different things as possible. Right, has anybody got a topic you want to start off with? Anything you want to go over and that we've covered in the last 11 weeks that you would think you might benefit from? I mean, I'll start somewhere, but it's nicer if you tell me.
I think lines and planes.
Right, I'm getting that stupid wobbly thing off these thinking earphones. Hold on a minute, I'm going to try something. Okay, I just did the old switch it off, switch it on thing. So, Eric, you were saying something, but it was that garbled, I really couldn't hear what you were saying.
I was gonna say lines and planes.
Lines and planes, gotcha. Let's do that.
Yeah, it's just like the geometry of it was a little hard for me at first.
Sure. So, a plane is basically a flat, infinite piece of paper in 3D space. All planes have a general equation. They look like this. This is just an example of something. They are linear combination of x, y, and z equals a number. So if you ever see an equation that looks like that, it's a plane in 3D. That's what a plane looks like. Now, if you add in some axes, it might help. That could be the z-axis. There would be my x-axis. And there would be my y-axis. So a plane would be like this guy. See this guy here? You imagine bending at a weird angle, can go on forever. That's what planes look like. Now, if you do a line in 3D space, and we're talking about 3D space here, a line could simply be this guy. That's a line. Now, if you want to tell someone the equation of a line, that basically is, tell me a way of finding every point that would lie on this line. They typically are written down in a number of ways. This first way I'm going to show you, just a random example of what it might be. Would be in that format. Now, if you write it in that format, it's sometimes called its parametric equation, right? And that represents, for any given value of t, you will find one point on this line. And when you write an equation like this, the line has an orientation. What that just means is that you travel up the line or you travel down the line. So if you wanted to know what the orientation was, couldn't you find out where it was at t equals 0 and then where it would be at t equals 1, and you'd find out, let's just say for argument's sake that the line's going this way. Now we have two different types of questions related to this. One question would be that you would get information and the question would be find the equation of the plane. And the other would be you'd be given some information and you've been asked to find the equation of the line. There are two types of questions. The next kind of question that you might get is, how does this plane interact with this line? Now, in my picture here, doesn't it look like I've shot a hole through it? Right? The line intersects the plane once, but there are other things. Couldn't the line float above the plane, so never touch it, right? We would say it was parallel to the plane. Okay, imagine, where's my cardboard? Here's my plane. My pen is my straight line. Do you see that you could fly and never meet it? Now, if I bend it at an angle, isn't it going to pierce the plane, shoot a hole through it, and then travel the other side and never meet the plane again, right? Geometrically, if that happens, it's only going to be in one place. What would be the third situation? How could a line and a plane interact? One is you fly above me, you're parallel. One is you hit me. But what was the third thing that could happen? Couldn't your line be in the plane? In other words, all the points on the line are the same, they're in the plane, right? It's a bit like that pen right now, see it? And we say it's embedded in the plane. So are the kind of things you want me to go over? How to find the equation of a plane when you're given information? How to find the equation of a line from certain information? Or how to find the intersection of the two? So I'm looking for a little bit more detail. What is it you would like me to do?
So yeah, I would like to know how they I don't know how they intersect, and I also don't know how to turn that equation up there, that x plus 2y plus 3z equals 6 into that RFT parametric equation.
Oh, you don't. These two are totally independent. They never do turn into each other.
Oh, really? Okay.
So a plane is a plane and its equation looks like this. A straight line is a straight line and its equation looks like this. So this guy does not turn into that. They are not connected. So you've picked up about an erroneous idea. But what I can show you, which is actually quite easy to do, is I can tell you how this line and plane interact with each other. So
yeah, that'd be cool.
If you write down the equation of a plane, that guy there represents the x coordinate or position of the line. That's the y coordinate, and that's the z. So this x gets replaced by 3 plus t. This y gets replaced by, well, 2 lots of y gets replaced by 2 lots of this guy. And lastly, 3z gets replaced by 3 lots of that guy. And it's equal to 6. So essentially, you substitute these 3 guys for the x, the y, and the z in the plane. So, and I put, that's a t, by the way. And what I'm going to do now is solve this equation, because this equation only has one variable in it, it's t. So I have 3 plus t, 4 take away 6t, add 15t equals 6. And then if I collect like terms, 3 and 4 gets me 7. That guy, and that guy, I believe, gets me plus 10t. Yep. And that guy there is still 6. And then I can subtract 7 from both sides. And then I can divide. And now I have what t is. And then to figure out what is that telling me, if t is a number, even an ugly fraction, it's telling me that we are going to intersect at that point. Now I'm going to find out what the coordinates at that point are. I just take the equation of the space curve, and it's 3 plus t, it's the first one. 2 take away 3t is the second one. And 5 times t is the last one. And that guy is basically 29 tenths. That guy is 3, so it's 23 tenths. And that guy there is -5 tenths, which is -1/2. Now we call these space curves, sometimes we say position vector. That is a position vector. That tells me the coordinates of this point. It's roughly at 29 tenths, 23 tenths, -1/2. So now I know the coordinates of where a line intersects a plane. And I do that by replacing the x, y, and z by the x, y, and z components of the position vector, this guy. Solve for t. Once I know what t is, substitute it in here to get the position vector, which in turn tells me the coordinates. Because position vectors are really just a way of telling you the coordinate of a point. And the reason why that works is this position vector is always the vector from the origin to that point. So if the vector from the origin to that point is this guy, then that must also be the coordinates of the point. Now, I said there were two other things that could happen. Couldn't we get the one where you fly above me, right, and never touch me, right? You would do the exact same calculation, right, that you've got here. And when you plugged in all the t's here, here, and here, and you tried to solve it, this is what would happen. Something like that. All the t's would disappear, right? So that 5t gets killed off by that 5t and nothing's left. No more t's, just a number. Now, 7 = 6 is impossible. It's not true. 7 is never equal to 6. Even if you work for the government, it's still not equal. What that tells us is that the shape is never going to meet the plane. So the line never meets it. So that is what parallel line stroke plane is. That's that situation. Now, the third and final possibility is, couldn't the line be part of the plane? In other words, the line is in the plane, like this. You do the exact same calculation again, only this happens. All the t's disappear, but the number that's left is that number, right? It's 6 in both cases. And that is true. And that's true no matter where on the line you go. So that must mean that we now have the line, fancy word for it, is embedded in the plane. That's quite different from sequences in series, right? Different, no connection, different piece of knowledge.
So where does 7 = 6 and 6 = 6 come from?
If you plug in these three guys here, 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 and here, in a different, I'd have to do a question of each situation, but essentially, can you imagine you plug these three guys into here, here, and here, and all these t's cancelled each other out, and all that was left was, say, a number 7 here. That's what I was saying, right? So yeah, I'd have to create a new question to make that happen, right? Because these are the ones we've got. But essentially, you do the same process, but if all the t's disappear and all you're left with is a number, right? So can you imagine that those t's weren't there? Could you see what you'd be left with is 7 = 6? You can imagine that's a +4t, that's a -2t, that's a -2t, all the t's are gone, right? That's what I was getting at. And if that did happen, that's impossible. Parallel. Right?
Cool, I understand. Thank you.
And if they disappear and the answer, i.e. the number here is 6 and it matches that one, then you're looking at embedded. And that's really the only 3 things that can happen when a line interacts with a plane. Does everybody know how many questions there are in the final? Because I'm pretty sure I mentioned it, but you may not remember.
20.
Right, 10 multiple choice, 10 section 2. Chronological order, right?
Yep.
So you know question 1's week 1, and you know the last question is going to be something to do with Taylor's series or something in that whole range. To give you an example, there's I think 11 sections in 11 sections in sequences and series. That's just sequences and series. You realize I cannot ask you every single question, right? Half the things you're going to study for, right, are not going to appear in that final, just by the sheer number of things that you could be asked compared to the number of questions you are going to be asked. But you have to assume, don't try and second guess me and say, oh, he's not going to do this or he will do that. Because I don't even know myself what's in the final because I haven't written it yet and I won't write it until this weekend. So who knows what, I do know that it'll be pretty evenly spread through a lot of the stuff with a little bit more from the second half because the midterms kind of covered a lot of the first half. But that doesn't mean I'll totally ignore the first half. It just means there'll be a little bit less from that half.
So are we allowed to use the graphing software and our notes?
Yes, graphing software is very useful and sometimes, no, let me take that. I was talking through a hole in my head, as they say. What is allowed, what's not allowed?
Is Desmos allowed?
Yes, Desmos is allowed. I'm trying to figure out a way of saying it so it won't lead you down the wrong path. The only software that you're going to be allowed to use is the software that you will find in Canvas in that one module that you will see. So if I put it in that module, you're allowed to use it. For instance, I will be putting the formula sheet in that module. So you can look at that, right? You know, things like, have I got one? Let's show you what I've got. That way I don't need to hesitate and say what I have and what I don't have. Let me show you what will exist on the day of the final. Right. Now, what you're looking at here, I believe, is the final exam information resource, right? This fella here, right? So that will be there because you need it, right? That won't be there, so that will disappear. You should know that, so that will disappear. That will be there because when you click on it, it'll be a PDF and that's where the questions are because they're not in WebAssign. That's where you'll upload your work to. There is the formula sheet that I was nattering on about. So can you see that top guy is Taylor's, just written down in a general way. There's the formula for the cross product. Not that most people would use that formula. Wouldn't you just cover up the eyes and do it by hand? But it's there. And there are some trig identities, right? So that will be given to you. And so that will exist. Let's go down a little bit further. That will disappear. That will disappear. How to upload, you probably keep that in case you forget. And these guys will be here, right? So let me blank these out for the time being and go into student view. Right, so that's what it's probably going to look like on the day of the final. Do you see almost everything is gone? So you won't be able to look at videos, you won't be able to look at homework help or anything else. Now, if you click on that guy, and can you see the fellas that are left alive? So that's what that is going to look like. Now, you will have your own written notes, I would assume and I hope, right? and you can use those. Right. What you're not allowed to use is, so you're not allowed to go onto the internet and just say, I'm going to go to a tutoring site and ask them how to do this question. And you're not going to phone a friend. And you're not going to use fancy software that does things for you.
Can we use the textbook?
That will probably have disappeared, so no, John. So you're
I-
going to
I-
have to,
I have the hard copy textbook. I use that for my identities.
that's physical, so I guess the physical's different. Yeah. WebAssign will essentially disappear. So if you've got something physical done, like you might have just written the notes, yeah, you should be able to use your textbook. Because if I said no, all you would do would write it down on a piece of paper and use the piece of paper, right? So it wouldn't really be, it would just be a waste of your time, right? Because you would still do the same thing, right? You just write it down. So I won't have a problem with you doing that. The reason I don't want WebAssign to be there is if you go into WebAssign, can't you do check me another, and you might find something like it, or check your homework, or do something, that is really a little bit too much help, because we really want to test what you know, not what you can find in a 3-hour period by looking up other people's stuff or your own stuff that you did in the past. So that's kind of what I'm trying to restrict from happening.
Well, as long as we can look at our own stuff, I mean, any of the hard questions in WebAssign I've done on paper.
So you're good then.
Yeah,
And you've still got between now and Monday to do that if you haven't done that. You probably want to write down the stuff you can't remember, because if you know how to do it, you probably don't need to write it down, right? You probably know it. But I mean, that's just my suggestion. You do what you wish, what suits you best. What else am I thinking about? Monday is going to be another school day, but it's very open-ended. I'm not doing any lessons on Monday, but if you choose to, you don't need to, but if you choose to, you can come and just ask me some questions. You don't know what you don't know, so you're going to be studying hard this weekend, I hope. And then you're going to say, oh, I didn't realize I don't know how to do X, Y, Z. And so you can drop in on Monday and say, can you show me how lines intersect with planes, Eric? That kind of question. Or can you show me how to get arc length? Right? I'm really stuck on that.
What
Whatever
time
that might be.
Monday?
It's usual time. It's going to be our 5 to 7 and a bit time slot.
Okay.
So you don't need to be here for that whole time period. If you want to be, that's fine. If you don't, I'm assuming that you're just studying on your own, and that's good. I have no problems with that. Right, any other questions? Right, let's look at some topics, and maybe that'll make you think about something. Oh, I'd like to know about that kind of thing. So here we go. When you see everything at once, there is a lot of stuff here.
it's a lot of difficult stuff too.
Yeah. So chapter 12, that's these guys here, right? Are basically coordinate systems, vectors, dot products, cross products, parallelepiped, lines, meeting planes, all that stuff. Is there anything in that general
Can
chunk of space?
can you do area of a parallelepiped and volume of a parallelepiped?
Well, there is only one of those two that actually happens, and that's the volume one.
Okay.
You can have area of parallelograms, and you can have volumes of parallelepipeds. Oops, hit the wrong one. I've lost my thought process. Here we go. So let's take the simplest one and then kind of work out from there. Imagine that you've got a vector
So
u. Yes.
real quick, the one that I was thinking of was like the one that was on the midterm where it had adjacent edges and not just a singular vector.
I'm trying to think what that would be.
I have it in front of me. I can read it off
Good.
to you.
Read it off. That's a good way
So
of doing it.
find the volume of the parallelepiped with adjacent edges PQ, PR, and PS.
Okay. And did they tell you what those vectors are?
Yep.
Okay. What are they?
P is 2, 0, 2. Q is -4, 3.
Oh. P is a coordinate, so 202.
Yeah.
Gotcha.
Yeah.
Q,
-4, 3, 6. R is 4, 1, 1. And S is 0, 4, 3.
so imagine that this is P, this is Q, this is R, and this guy here is S. Now, when you kind of add some extra vectors to this situation, you get one of those shapes, which basically is what a parallelepiped did. Isn't it like a box in 3D space? Now, the formula for calculating the volume of it is there's PR, there's PQ, right? There's PR, and here's PS, right? So there's the three vectors they're talking about. And if you want to get the volume, in general, the formula is U dot V cross W, sometimes called a triple product. You do a cross product of two of the vectors, and then whatever that answer is, you do a dot product with the other third vector. And you can actually mix and match who's U, who's V, and who's W. It doesn't actually matter. The answer ends up being the same. That is a scalar. That will be a number. Now, technically, they stick an absolute value around it, because if that number is -20, the volume is 20, right? If it's 20, the volume is 20, right? So if you see the absolute value around it, that's what they're getting at.
The absolute value around the cross product. Oh, there
No,
we go.
the absolute value around the dot product of this with a cross product. Now, in our world, the vectors are going to be, that guy can be my PQ, and then the other two guys are going to be my PR cross with my PS. So that's what the edges bit was about. They're basically, I'm trying to tell you, look, here's your three edges. Now, when you tell me the coordinates of something, you can find the vector joining them together. So for instance, to get the vector joining P to Q, you do that second take away the first trick. -4 take away 2 is -6. 3 take away 0 is 3. And 6 take away 2 is 4. Are you comfortable about how I got PQ? Right. Second take away first, right? Position. Yep. Right. Then to get PR, the next vector. Second take away the first, 2. 1 take away 0, 1. 1 take away 2, -1. And to get the last one, PS. Nothing take away 2. 4 take away 0. And 3 take away 2 is 1. So these three guys are going to go here, here, and here. There is a lot going on in here, so I'm going to do some guys at the side. Let's do the cross product of the vector PR and the vector PS.
So just real quick, I probably know it's probably an obvious question, is so that if, for instance, instead of it being -4, take away 2, if the signs were swapped where it was 2, take away -4, it would turn into 2 plus 4, right?
Yes.
Okay.
So we have I, we have J, we have K, and I have a formula in the formula sheet, but nobody uses it. So what do we have? We have a PR, so 2, 1, -1, and we have a PS, which is -2, 4, 1. And that answer is going to be so many I's. It's been a while since we did these guys, so many J's, plus so many K's. And then I do the cover up thing. Right, you want the I's. Major diagonal 1, take away -4, which means you add it, you get 5. Middle one, major diagonal 2, take away 2. Oh, 0. Last guy, major diagonal 8, take away -2 means you add it. And so we end up with a vector 5, 0, 10. And that's the cross product. That's this guy here. So what I'm going to do now is take PQ, which is the vector -6, 3, 4, dot product with that guy be. And that's a 5, 0, 10. And the dot product is you multiply the x's together, plus you multiply the y coordinate, the y values together, plus the z values. And I get -30, add 0, add 40. And the answer I got here is 10. Since that answer is positive, I don't need to worry about the absolute values, right? The answer is going to be 10. If this happened to be -10, then the absolute value thing would kick in and we would say the volume is 10. Volumes are physical things. They must be positive, right? Nobody would say the volume of that box is -10. Right, that would be weird, right? It has no meaning. Now, side issue. These three guys can be interchanged any way you like. So for instance, I did PQ here and the other two there. I could have made this PR and put the other two here. I could have made this PS and put the other two here. And although the numbers individually might look different, the final result would be 10 in each case. So it's not that important that you remember which one goes first, second, or third, right? It doesn't really matter. What does matter, however, is that they all must start at the same point. So you noticed I started at P to Q, P to R, and P to S. That is important, right? Because you have to project from a single point to get that guy. Okay. Now, indirect to that. Suppose we did a calculation and the answer to, let's call them U, V, and W. So pretend this is a different question now. Nothing to do with parallelepipeds, but just finding that. And we got the answer 0, which could happen. How would you interpret what that means? How could you get 3 vectors that look like these, evidently, but you get a 0 for the answer? Any thoughts? How could that happen? Because there is one way and only really one way that's
You
not true here.
start at A and come back to A.
Oh, that's like doing a little route back to where you came from.
Yeah, like I would say there's no volume, right? So
Right, you're right, there's no volume. Imagine this was U, and this was V, and this was W. So you couldn't really come back to where you started. But nonetheless, those 3 guys still made 0 volume. How on earth could that happen? Oh, here we go. They're all on the same flat piece of paper. So basically, wouldn't you just make a flat thing, and a flat thing has zero volume? It may have an area, right? But it has zero volume. And we call that, when it happens, we say that the vectors are coplanar. So if you ever have 3 vectors and you do this calculation and the calculation is 0, you can be pretty sure that those 3 vectors are actually all on the same plane, right? And if you imagine a flat piece of paper, all 3 would be drawn on that same flat piece of paper. Right, let's move over, and maybe some other things will come to you.
We would just label the 10 with cubic units, right?
Yes, it'd be cubic units for the parallelepiped since it's a volume.
Would we lose points if we forgot to label the units?
Probably not. I'm not an engineer, so I'm fussy about style points, but I'm not that fussy about units. Right, now, the next chapter 13.
Would you mind doing number 9 on the practice exam?
I don't have it handy. Is it something you can read out to me quickly?
Yeah, it says the length of the arc for the curve x equals 1 plus 3t squared, y equals 4 plus 2t cubed
Mm-hmm.
from t equals 0 to t equals 1.
Okay. And is that a multiple choice question or a section 2 question, just out of curiosity?
It's a multiple choice.
Oh, okay. So were the answers in the form of an equation, or were the answers in the form of a physical number for each?
Physical number. And then there was
Okay.
2. One was undefined, another was some other answer.
Okay, so
I don't really need you to go over the whole problem, just kind of like the method, how approach you do it.
right, so let's pretend that I was a student and that was an exam question, right? So I'm going to nip back to the formula, the place we are, right? So I'm going to have to move back out of here. And I'd say, well, let's go into student view because I'm pretending to be a student here. And I'd say, oh God, there's an arc length formula. I know there is. I can't remember it. So I'm going looking for it. So I'll click on it. And the arc length formula that I want to use is this guy here. You see it? So I would write that down as the integral from a to b. And then it's the square root of f dash t all squared. And then it's plus g dash t all squared. And then it's a dt. So I'd have a look just in case there was some other arc length formula. And the only other arc length formula they've got is in a space curve where there's 3 guys, right? There's 3 pieces. And the one I've got up here is an arc length formula with 2 pieces. So I'd look at my question and say, my question only has x's and y's in it, right? So I would be using the 2-piece one. If it said x is this, y is that, and z is t cubed, then I'd use the 3-piece one. They're very similar looking formula. So that would be the beginning of how I would be doing it. So I've identified the correct equation, which is this one. I just have to remember that this guy is called f of t, and this guy is called g of t. So that way I know who's who. And then that guy is A and that guy is B. So I put the pieces together. I'm going to go 0 and 1. I'm going to differentiate that guy, which I believe is what, 6t, and square it, because that's what you told me to do in the formula. I'm going to take this guy, and I believe he's also 6, but I think he's 6t squared, and then I square it, dt. So I'm assuming that you got to something that looked like that, John. Is that right? Do you remember what you did, or did you not get to this?
I tried using s is equal to the integral from a to b, the absolute value of r prime of t dt.
Okay, that's actually the same thing. It's just written down in a different format. It ends up being the same thing.
It just didn't have
So-
the square root in it. So
Well, when you are finding the magnitude of r dash t is this guy. And when you find the magnitude of it, it's the square root of this guy squared plus this guy squared. And the dt part is still there. So you see it's the same guy.
so what is r of t? Maybe I'm missing something.
Yeah, r of t is
It's gonna be x and y, x plus
Yeah.
y.
x and y.
Okay, so really it's r squared plus x squared plus y squared, and then you take the square root of the x.
Yeah,
and
and x is turned into t's and y's is turned into t's, and you differentiate them before you do that. So in this case, you've got the integral from 0 to 1 of 36t squared plus 36t to the 4. It's funny, my pen's gone. dt. Right? Are you comfortable? That's your f. That's the derivative of it, and that's what you get when you square the derivative. This is your g. That's the derivative of it, and this is what you get when you square it. Now, if you look at that integral, it's very easy to make a big mistake. And the big mistake is, oh, I'll just take the square root of that plus the square root of that and get, I don't know, 6t plus 6t squared, right? Looks really nice. Wish it was true. It's not. This integral is not as nice, and it's not as obvious right now how to do it. Has anybody got any suggestions for what I'm going to do in the next line that would allow us to work with this a little bit more to get it into form that's going to allow me to integrate it? Because right now I can't integrate it.
You have to factor, I think.
Yeah, you do. What's the best factor? Well, I think 36t squared is the best factor. And you get that guy, right? And then you have to do kind of another piece of algebra. And the next piece of algebra is to realize that square roots that are multiplied can be separated. This you are allowed to do. And you have to trust the math, because sometimes things look like they're going, you know, they're going down this road that's going to lead nowhere, but it is going to get you somewhere. Because that guy is 6t, and that guy, I'm not going to do anything to. So the original integral, which was really a dead end, with a bit of algebra, I get to here. Now you've got one more leap, one more thing to do, and that is, how do you integrate this fella? Well, there's a process, isn't there? And what would it be? How would you integrate that? You don't need to know. Hopefully you remember the name. Even if you don't, I guess you could tell me what to do.
Substitution.
It's a substitution. And the u sub would be 1 plus t squared. Do you want me to keep going, or do you basically, you know where that's going to go from there?
Yeah, I'm good. I'm really
Right.
good. That's awesome. Thank you.
Right. So I think your problem was that there's what's that phrase? There's more than one way to skin a cat. In other words, the arc length formula can be written in a variety of different ways, right? When you write it with this format, you have to realize that that's basically the x and that's the y, right?
For some reason, I did not connect r of t to be equal to x squared plus y squared. I don't know why I didn't connect that, but I just didn't. I just was like looking for, where's my r of t?
Right. Well, if you were thinking of where's your r of t, it's 6t. No, it isn't. Start again. It's 1 plus 3t squared and 4 plus t cubed. There's your x, there's your y. And if you differentiate this guy, there's that 6t, And there's that 6t squared. If you find the magnitude of this guy, that's where the kind of x squared, I think you were calling x squared plus y squared comes from. And you see that's where this bit comes from. And so the arc length can be written as integral from 0 to 1 of the magnitude of the derivative guy, dt, which is the formula that you found. And that guy is this fella. Right? Just a different way of looking at it. Cool.
I would appreciate if we could finish that question, actually.
Not a problem. So at this point in time, I'll just write it up here because we'll start. We have a 6t square root of 1 plus t squared dt. And I'm going to do a substitution of 1 plus t squared. So if you differentiate that with respect to t, you get 2t. Do what I call the crossover, and then divide both sides by 2t to isolate the dt. So this integral now becomes 6t, the square root of u. The dt becomes 1 over 2t du. If you do things and things come out well, you get a lot of cancelling. And now my integral becomes 3 square root of u's, du's, which is pretty easy to integrate, but I need to convert it into a fractional power. So I can use the power rule, which is add 1 to the power, 3 halves, and then divide by 3 halves, which is the same thing as multiplying by 2/3. 3 times 2/3 gets you 2. You then turn the u back into 1 plus t squared. And then you can evaluate it at t equals 0 to t equals 1. And if you plug in 1, you get 2 lots of 1 plus 1 squared is 2, so you get 2 to the 3 halves. And if you plug in nothing, you get 1 to the 3 halves, which is just 1, so 2 times 1 is 2. And then you want to make it look pretty. 2 to the 3 halves is actually 2 times 2 to the half, so it's actually 2 root 2. And so I guess the best I can do is 4 root 2 take away 2. And that hopefully is one of the choices that you got in the multiple choice.
It is.
Okay. Good question. Like it. See where else we can go. Hopefully those who drop in on Monday may have some other topics, other questions that we can talk about, but we got the time, so let's use it right now and look at, I've forgotten the darn thing. I'm going to have to leave student view. I think I've hidden one of the things I want to look at. There we are, found it. Okay. So we just did a question, for instance, on arcline. Motion in space would be, r dash of t, and find velocity, acceleration, speed, that kind of question. We'd also get things like the tangential and normal components of acceleration would fill, that would be in that area as well. We move on to 14. We're dealing with the partial differentiation stuff here. Well, the beginning isn't really that big, what is a multivariate function and how do you find the limit as x, y goes to 0, 0, that kind of thing. The more important stuff is the partial derivatives. How do you differentiate a multivariable function, and then the chain rule. That would be things like z equals x squared plus y squared, but x is 2t plus 1 and y is 4t minus 1. And how would you differentiate with respect to t in that situation? That's kind of what the chain rule does. And then we have everybody in sequences and series. We get any topics that we're looking at that you might want to, or any questions from the practice paper or whatever?
Yeah, can we go over some partial derivatives?
Sure. So let's look at how to find partial derivatives. The trick to doing partial derivatives is if you have the ability to realize that at any given moment in time, only one of the letters, only one of the variables is truly a variable. All the others get considered as if they were numbers, which we call constants. So you might have a function like this: z equals x cubed y minus y squared x squared plus 4e to the x. There's a multivariable function, right? It contains x's and y's. And a partial derivative has a couple of notations. One of them you write like that with a little curve d. Another way of asking it is z with a little baby x, right? That's common notation. And suppose I wanted to find the partial derivative of this guy here, right, with respect to x. So you take each thing and you differentiate it with x as a variable and any other letter, treat it as a constant. So x cubed y, well, if I differentiate x cubed, it's 3x squared, but there is a y there. So the answer is 3x squared y. Because if I went and said to you, differentiate 5x cubed, wouldn't you still have a 5 there, right? You'd still keep the 5, right? You just go 5 times 3 and get a number. Now, if you move on to the second term, what would you get if you differentiate y squared x squared with respect to x? What would that guy be? Differentiate as if x is the only variable in time. Any takers?
Minus 2y squared times x.
Yes. And then what about 4e to the x? What do you get if you differentiate that with respect to x?
Is that just 4e to the x?
Yeah. And I just put in an extra guy for fun. What would you get if you differentiated y squared with respect to x? So be careful, this is sneaky. What would you get if you differentiate y squared with respect to x? And the answer is not 2y.
It's just 0.
Big fat 0. It's just like somebody said differentiate 5 squared. Oh, it's still a number, right? 5 squared and 25 are the same number. Right. Now, if you do the same z, but now differentiate with respect to y, you will not typically get the same answer, right? You would expect a different result when you choose y to be the variable and consider everyone else to be a constant. So back to the first guy again. X cubed y is a bit like somebody saying 5y. If you differentiate it with respect to y, you get x cubed. If you differentiate this one, you get 2y x squared. If you differentiate 4e to the x with respect to y, partial derivative, I should say, you get, oops, you get big fat 0. And if you differentiate that guy, you get 2y. So the answer, because nobody writes zeros down, so the answer would be written like that. Cool.
There was a more complicated one where
Mhm.
you couldn't get the z by itself.
Implicit differentiation, it sounds like, yes?
Oh, implicit, yes. Yeah, that's a
Okay.
tough
So
one.
let's make that one you can get without that trouble. Let's suppose you got z cubed equals x squared minus xy cubed, right? Let's suppose we had that. And the question asked you to find dz by dx. Right? So implicit differentiation should only be used when the formula is not z equals. So if it's z equals, this is the way to go. But if it was a z squared here, or x squared plus y squared plus z squared equals 10, you know, something like that, then you would do this different technique, which is called implicit differentiation. If you differentiate z cubed with respect to x, you will get 3z squared dz by dx. And that comes from implicit differentiation in Calc 1. Can you remember doing the same name, implicit differentiation? Y cubed would get you 3y squared dy by dx. Remember that kind of thing? That's what's happening here. Right? And the reason for that is that in these questions, x is a variable, but z is considered to be also a variable that has x's in it. So when you differentiate it, you get 3z squared times dz by dx. Now, if you differentiate this guy, you just get 2x, because everybody gets differentiated with respect to x. And then you differentiate this guy with respect to x, and you get minus y cubed. So this guy gets you 2z cubed dz by dx. This guy with respect to x gets you 2x. This guy with respect to x gets you that. And now, your ultimate goal is to separate out dz by dx, right? So what would we do next? It's a one-liner.
And I'm just divide the 3z squared.
Apart from the fact you called it z, you were perfect. It's 3z squared. Got to remember to pronounce things properly. And that's implicit. That's an example, at least, of implicit differentiation. Does that help you with the one you were looking at, or do you want me to do the one you were looking at, if you were looking at a specific one?
I guess I'll come back to it Monday if.
Okay, we
if
can
this
do it
isn't
Monday if it
sufficient.
ain't
I
working.
appreciate it.
Okay.
Thank you.
Okay, have we any other questions for today? As I say, I'll be here on Monday. Can't guarantee I'll be available all this week, but you can certainly send me emails, and as soon as I have a chance to read it and then make up a reply, I will send you a reply. There's nothing more frustrating than, you know, waiting a long time just to find out, you know, one little thing that's stopping you from finishing a question, for instance. Okay, then. The test is available. It should be, at least. Anybody want to double check? Can you see the test? Online
Yes.
test 10.
It's
Right.
there.
Right. It's the same. It's the same as before. It's kind of 2 weeks worth of work, isn't it? Really? Well, a week and a bit. It's everything is due on Sunday. There are no extensions from now on. You never got an extension for online tests anyway. Sometime on Monday before I see you, I will have double checked the online test. I would have put in your homework grades, and I will send you out one last report. And in that report, I will tell you what you need to do in the final out of 300 points to get a 2.0. That's a pass, a 3.0, or a 4.0, whatever you're interested in. Okay.